For these sets of lessons, lessons 1.3, we're going to be talking more about current in circuits. So electric current, the symbol used is an I. Sometimes it's lowercase, sometimes it's capital. And your book tends to use a capital I for the current. Is defined as the rate at which charge flows. So charge is moving in a conductor. So imagine a long wire where charge is moving along that wire. How quickly charge moves is defined as the current. So the current is equal to the change in charge over change in time. Where delta Q is the amount of charge that passes through some area in an amount delta T. The unit for current you've probably heard before, unit for current is the ampere, often substituted or abbreviated as an amp. An amp, 1 amp, and a capital A is used for the abbreviation for ampere. 1 amp is equal to 1 coulomb per second. So again, SI units. Ampere is the SI unit for current. It is one of the fundamental SI units, actually one of the 7 fundamental SI units, along with mass, time, temperature, length, the meter, right? So 1 ampere is 1 coulomb per second. The direction of the current is the direction that positive charges would flow. Now this adds some confusion when talking about circuits, because we know at an atomic level, positive charges are trapped in the nucleus, and it's the electrons in the cloud orbiting the protons. Those electrons are the things that move in a conductor. Electrons move. However, it wasn't known when these definitions were made if it was the positive charge that was moving through a conductor or the negative charge that was moving through a conductor. So the current, again, how positive and negative charges was defined by Benjamin Franklin, it's arbitrary. That protons have a positive charge and electrons have a negative charge, that was an arbitrary distinction. Franklin could have said electrons have positive charge and protons have negative charge. Or Franklin could have said, I'm going to call this dogs and cats, or north and south, which we use for magnets rather than electric fields. So note that the direction of the current, while it's the electrons that move through the wire, we pretend it's the positive charge moving in the opposite direction. So the current is in the direction positive charge would flow, which is opposite the direction negative charge does flow. So we pretend it's positive charge carriers moving in a conductor, even though we know it's not. Now, when charge flows, the current is not defined as the individual speed of the atoms or the electrons in the conductor. In a conductor, conduction electrons are very weakly held. They're basically free to move about like air molecules in a room. The electrons are trapped in the conductor, but they're free to move about within that conductor. They move incredibly quickly, but they move in random directions. So the current is related to what's called the drift velocity of the charges. Drift velocity is just the average velocity of the free charges. It's much, much, much smaller than the speed of a single electron. An analogy from last semester, that might make more sense. In the room I'm standing in right now, there is no airflow, right? There's no wind. So the average velocity of the molecules in this room, not the average speed, but the average velocity, it's a vector, of the air molecules in this room is 0. But the air molecules in this room, that doesn't mean they're not moving. The individual molecules are moving very fast, hundreds of miles an hour, thousands of miles an hour for some. And they're moving in random directions. So if I were to, say, set up a fan at one end of the room and push the air through the room at a slow rate, let's say I got a 3-mile-an-hour wind in this room, or you stand outside and there's a 5-mile-an-hour wind passing you by. That 5-mile-an-hour wind is the average speed of all the air molecules around you, which are still traveling incredibly fast. Now, in a conductor, while the individual electrons are traveling ridiculously fast, they can travel upwards of 10 to the 8 meters per second. To give you a reminder, the speed of light is 3 times 10 to the 8 meters per second, so that's up to 1/3 of the speed of light. The drift velocity, when you actually think about the current that's flowing in the wires from your power plant to your house, the speed of those electrons is about 10 to the minus 4 meters per second. That means that it takes 10 seconds for an electron to go an average of a millimeter in a wire. So the electrons themselves don't flow very quickly. The electrons themselves move very quickly, but the electrons, the bulk speed of the electrons through a wire is actually quite slow. So the current is related to this drift velocity, not the velocity of the individual atoms. So think of drift velocity like, again, wind. What direction is the wind? Wind is an average speed of all the air molecules around you. The current is the average speed, right, the amount of charge on average that passes through some time t. Now we'll look quickly at how current and drift velocity are related. But first, your book talks quickly about, in general, things that are good conductors of electricity are also good conductors of heat. And the way to think about that is things that are good conductors of electricity have free electrons. Those free electrons are free to flow. So it's easy for electrons to flow through the material. That material is an electrical conductor. If it's difficult for electrons to flow through a material like glass or plastic, those materials we call electrical insulators. It's why we use rubber on the outside of a wire. If you've ever seen a cable gone into your basement and seen wires running out of the box, we don't use exposed wire, although they did a long time ago. We use a type of cable called Romex, which has a plastic rubber sheathing around it, and the metal conductor is inside. Since rubber is a bad conductor, you can grab a wire that is live, if it has a rubber coating and is not too high voltage, and not kill yourself, right, and not get shocked. Not recommended, but you can do it. So things through which electrons flow easily are good electrical conductors, but they're also good conductors of heat, because remember, heat is, from last semester, molecules bouncing around one into the other and bumping into one another, giving the energy, transferring the higher kinetic energy from the hot side and moving it across to the cold side. Right? That's the point of a conductor. If you've ever thawed chicken or a burger from the freezer, right, the warm room air, if you thaw it in the room temperature, which isn't recommended, the warmer air of your fridge then compared to the frozen chicken warms the outer part of the chicken first. It takes a while for the heat to get in, or just baking something, right? Baking a casserole or a turkey, the outer part heats up before the inner part, because you have to conduct the heat through the material. Well, things that are good electrical conductors have the free electrons. Those electrons, since they're free to move through the conductor, take that kinetic energy and fly through the conductor and bump into things way on the other side. They're really effective at distributing heat, which is why if you've ever cooked anything, the pots and pans you use are metal, right? Metal is a wonderful conductor. You have a copper bottom, you might have copper set, you might have a tin set, unlikely. Aluminum is a popular, cast iron, right? Wonderful conductor of heat, big old cast iron skillet. So things that are good electrical conductors are also good heat conductors. Now, going back to electrical current and drift velocity. So here I have a cross-section of a wire drawn. Imagine taking a thin wire, cylindrical little thread of wire, and blowing it up. So it has cross-section A. It's a big cylinder of metal, or say big, but we've zoomed in on it, so it's a cylinder of metal. It has some length x, and we want to know how much charge flows through this area in time delta t. Right? That's the definition of current. Current is the amount of charge that flows through some point in a given time. Well, how do we figure out how much charge can flow? Well, it's a little more complicated. We have to break it down. First of all, we need to know how many free electrons are there in a given volume of space. Well, we know the volume of this is just a big cylinder. So using the cheat sheet that I've provided online, or Googling it, your book will have this as well, or remembering your geometry, the volume of a cylinder is the area of one side times the length of the cylinder. So the volume of this cylinder is A times X. That gives you the amount of total volume of this conductor. But the volume doesn't tell you how much charge there is. But if you know what the density of charge carriers are, right? How many charge carriers you have per unit volume, which we represent by N here. So N is the density of free charges. Density is number of things per unit volume, right? Mass density is mass over volume. Number density is number over volume. So this is the number of charge carriers per unit volume multiplied by the volume. So these terms, N times A times X, gives you the number of charge carriers you have in that area, or in that volume. Still doesn't help you though, because we need to know how much charge passes in that time. We have the number of charge carriers, but how much charge does each carrier have? Well, that is Q, right? The charge on an electron. So N is, you can think of the number of electrons per unit volume. X times A is the volume. So when you multiply those things together, this term here gives you number of electrons. When you multiply the number of electrons by the charge per electron, you get the total charge. The total charge over the time, in this case delta T, gives you the current. So this equation here on the right, the total equation, is the current in this wire. Well, I rearranged it a bit. Q times N times A, that's still the same. I moved the delta T over here with X, and I grouped that together. Because that's what's changing with time, right? The position is changing with time. The density doesn't change with time. The density of charge carriers is the same throughout the whole material. The charge on an electron doesn't change with time. It's always the same. The cross-sectional area of this wire doesn't change with time. The area stays the same. So the only thing that's changing with time is the position of these charge carriers as they move. Well, position over time is velocity, right? How far you've gone in a certain amount of time is the velocity. In this case, it's the drift velocity. So, if you want to know the current in a wire, it's related to the charge on an electron, the number density of charge carriers or electrons in the material you're using. This Q always stays the same, right? Q is the charge on an electron. That's 1.602 times 10 to the minus 19 coulombs always. All electrons have the same charge. They're ubiquitous. You cannot tell one electron from another. They're identical in charge. N is the number of charge carriers. That varies depending on the wire, right? Aluminum and copper might have different charge carrier densities. One might have slightly more electrons per unit volume than the other. All of them would have high electron densities, free electron densities compared to plastic. For example, plastic is a terrible conductor. It doesn't have many or any free electrons per unit volume. A is the cross-sectional area of the wire. So the bigger the wire, the fatter the wire, the bigger the current. Think of it like a hose, right? A garden hose versus a pipe that leads water to your house. If you've ever seen water utility companies, the huge pipes that go into water treatment plants, because the bigger the diameter of that pipe, the more water that can flow, the higher the current of water, if you will, the higher the flow of water in a larger diameter pipe. So the bigger the area of that pipe, or in this case the circuit, the higher the current can be. And the drift velocity of the charge carriers. So if the current is 0, Q is never 0. Q is negative 1.6, 02 times 10 minus 19 coulombs. Excuse me. Right, that's the charge on an electron. N is never 0. That's the charge carrier's per unit volume for a conductor. That's never 0. The cross-sectional area of this wire is never 0. The wire has some cross-sectional area. So if the current is 0, that means the drift velocity is 0. Again, think of it like wind, right? There's no wind in this room that I'm in right now because the average velocity of all of these particles in the room is 0. Individually, the particles are moving quite fast, but when you add them all up vectorially, add up all the velocities, the net velocity is 0. So the current is related to the drift velocity.